Yo empiezo.
Okay.
Hello. We are going to show you how we would model a differential equation based on the case of the physical phenomena that bungee jumping provokes. First, we will start by analyzing what happens from the moment a person launches themselves until they reach their lowest point. And the plan for this analysis is to segment the processes into intervals of two phases for modeling, since the trajectory of a bungee jump can be broken down into three intervals associated with the prevailing forces acting at each moment: the free fall, the stretch, and the recoil or rebound. So the phase one, we'll consider the free fall, and the phase two, the stretch and the recoil. Now, the calculations, the phase one regard the length of the rope, the gravity, the mass, the rope's elasticity, the air resistance, the initial position, and the initial velocity. These initial conditions are set at zero, and the coefficients are determined along with the calculations in the further procedure. Now, these are the body diagrams, and these are the sum of the forces of how we will conceive the system. And it is important to state how we are modeling these equations, since these models can be made considering or not considering air resistance. Now, the calculations for phase ones are the following.
Okay, so for the calculations basically are we're solving a second order differential equation, non-homogeneous one. And the first part would be solving the homogeneous part of the equation, that is taking the roots of the uh, complementary solution. And we get that the first root is 0 and the second one is minus 0.00875. And then we calculate the non-homogeneous part of the equation using undetermined coefficients. And here we multiply by a t, because in the complementary solution, the C1 is the same as the proposed solution. So we need to multiply by t. So we make sure that we get a solution for the non-homogeneous part. And doing the calculations, we get that the particular solution is 1,121.14286 times t. And then for the general solution, we add the both parts, and we get this expression. And we use the initial conditions that were given, that it was that the position at the time 0 was 0 meters, and the velocity at time 0 was 0 meters per second. And by doing the calculations, we get that both of the coefficients have the same value, only they have different their sign. And we have the particular solution, and its graph is this one. In this case, we only consider relevant the positive part of the graph, because using negative values of time makes no sense.
Now for phase two, that considers the stretch and the rebound, the variables are going to be the same, and the free body diagram now looks this way. But now the forces, the sum of forces are only considering the y axis, since it's just free fall after the free fall.
The calculations for the second part basically are the same as the previous in the previous part, but the difference here is that we need to calculate the value of the coefficient of elasticity, and we do so by making the sum of forces that are the weight of the object in free fall. It's drag force that experiments, and it goes opposite to the direction of the free fall, and the elastic force that as the same as the drag force, it goes in the opposite direction of the weight. We isolate the x, I mean the k, And by substituting with the data that we have, that is the mass, the gravity, the drag coefficient, and the velocity at that time, dividing by x, that is the elongation of the rope or the cord when it starts from phase one until it reaches its maximum value. And in this case, we considered 105 meters because we assumed that the cord elongates more or less like 2.5 times its natural length. That is that if the cord is 70 meters, that is the value that we use. 2.5 times is 175 meters, and the difference is what we're letting x be here. That is 105 meters, and the elasticity coefficient was 7.22994. And we simply, well, in this case, we use a cast to do these calculations, and we get that the general solution was this one, the second one. And by substituting with the initial conditions that were the final velocity at phase one and the natural length as the initial position of the cord, we get that the particular solution is the last one, and this is the graph of that equation, which basically explains how it behaves when it starts to going down and up because of the cord that is stretching and slacking.